Some revolutions begin in silence, not as disruption, but as rearrangement, so quiet that years later, we forget a change ever occurred at all. By the middle of the 20th century, mathematics was powerful, yet fragmented. Topology spoke in shapes, analysis spoke in equations, geometry spoke in curvature, algebra spoke in symbols. Each field advanced with confidence, yet rarely spoke to the others. There was no internal mechanism to translate the behavior of equations into the shape of space itself.
As a result, mathematicians could describe structure or behavior, but rarely both at once. What mathematics lacked was not strength. It had strength. What it lacked was a unifying grammar. And beneath this absence, a young mathematician was not preparing to compute the next theorem, but to redesign the foundation beneath them all. At the time, almost no one noticed. Michael Francis Atiyah was born in London in 1929 to a Scottish mother and a Lebanese father. His childhood unfolded across Sudan and Egypt before returning to England, an early exposure to systems that did not naturally align. At Trinity College, Cambridge, he studied under William Valence Douglas Hodge, one of the most influential geometers of the century. Hodge shaped Atiyah's discipline, but not his direction. From early on, Atiyah was not drawn to calculation. He was drawn to structure. He was less interested in solving individual problems than in understanding why entire classes of problems behaved the way they did. At the Institute for Advanced Study in Princeton, his intellectual circle expanded. There, he worked alongside thinkers such as Isidor and Raoul Bott, mathematicians who recognized, as Atiyah did, that progress occurs not when fields compete, but when they align. Atiyah was not searching for results. He was searching for reasons results must exist. This distinction would define everything that followed. In 1959, alongside Friedrich Hirzebruch, Atiyah introduced topological K-theory. Topology possessed invariants, quantities that remained unchanged under deformation. But it lacked a systematic way to classify vector bundles, geometric objects that describe how spaces twist, connect, and carry internal structure. K-theory resolved this absence. It converted geometric complexity into algebraic clarity, allowing mathematicians to study shape without reducing it, not by approximation, but by translation. At the time, the importance of this idea was not fully understood. Even its authors could not yet see how far it would reach. Then, in 1963, came the work that changed everything. Together with Isidor-Singer, Atiyah proved what would become known as the Atiyah-Singer index theorem. Elliptic differential operators describe fundamental phenomena: heat flow, wave propagation, curvature, quantum behavior. Yet explicit solutions to these equations were almost never attainable. This was not a technical inconvenience. It was a structural barrier. Atiyah and Singer showed that the number of solutions could be determined without solving the equations at all. Every such operator, they proved, carries a topological signature, an integer extracted using K-theory, that exactly equals the analytical result mathematicians had struggled to compute directly. Analysis and topology, once distant disciplines, were revealed to be reflections of the same underlying structure. Classical results, once seen as separate achievements, Gauss-Bonnet Riemann-Roch, the Lefschetz fixed-point theorem, were now understood as manifestations of a single architectural principle. The index theorem did not solve equations. It explained them. In 1966, the Fields Medal Committee did not reward a collection of results. They recognized a transformation. Atiyah received the medal for the creation of K-theory, which reorganized topology and geometry into a shared language. The index theorem, which unified analysis with topological invariance. And his fixed-point work with Bott, extending classical formulas into universal structure. This was not a medal for progress, it was a medal for infrastructure, and infrastructure, once built, is rarely noticed until everything depends on it. The consequences unfolded slowly, then everywhere at once. Topology and geometry adopted K-theory as a foundational tool. Index theory became essential to modern classification problems. A new generation of mathematicians began working inside the framework Atiyah had built. Among them was Simon Donaldson, who applied these ideas to gauge theory, revealing that four-dimensional manifolds possess structures far richer than previously imagined. At the time, this seemed like a purely mathematical development. Only later would physics arrive at the same bridge from necessity. Gauge theory and quantum field theory required tools capable of classifying fields on curved, symmetric, and topologically complex spaces. Index theory, developed decades earlier for abstract reasons, became central to understanding anomalies, conservation laws, and field configurations. Mathematics had prepared the structure long before physics knew it needed it. The most powerful consequence of Atiyah's work was not that it solved problems. It dissolved the boundaries that made it necessary to explain the boundaries at all. Atiyah believed mathematics advanced through alignment, not force. Structure before calculation, insight before proof. He often spoke of beauty in mathematics, not as ornament, but as navigation, a signal of deep correctness, a compass rather than a decoration. And so we return to the question, now answered implicitly by history itself. How did one mathematician reshape mathematics so deeply that even physics was still tracing the consequences decades later? He did not do it by solving the most famous problems. He did it by resolving the most foundational absence. His work was not a chapter added to mathematics. It was a support beam inserted beneath all chapters. Some contributions are not meant to be seen immediately. They are meant to hold everything else together. Atiyah did not announce a revolution. He built the coordinate system in which modern mathematics could finally recognize itself as unified. His legacy is not the thunder of change, but the permanence that followed it. And in mathematics, permanence is the highest form of consequence. If you believe stories like this deserve to be told, don't forget to like, subscribe, and share this video. This is Awards, where the world's greatest minds live forever. Don't just watch history. Be inspired by it.